Good evening, all. In the previous video, we have seen about the introduction of the laser, principle of the laser action, what are the types of properties that are available for the laser, how we are going to differentiate the laser light with the ordinary light, and what are the types of emissions and absorption, and how the laser action is being done there inside the medium, and what is optical resonator, and what are the types of mirror that are there in the optical resonator. These are the things that we have already discussed in the past videos. In the current video, we are going to discuss about the types of laser, their principle, their construction, working, and their advantages and disadvantages. For our syllabus, we are having two lasers. One is carbon dioxide laser, and another one is a semiconductor laser. In the video, we are going to see both the type of laser, their principle, and their characteristics and their working mechanisms. Okay. Now we proceed with the carbon dioxide laser. So the principle is an active medium. Here carbon dioxide and nitrogen and helium is the active medium. All these gases contributes as an active medium. The nitrogen atoms rise to the exit state where they deliver the energy to the closest carbon dioxide atoms. So as a result of energy delivery from nitrogen to carbon dioxide atoms, the transitional and vibrational states of carbon dioxide molecules gets excited. As a result, laser beam will come out from the carbon dioxide laser. So the characteristics is given here. So the type it is a 4-level molecular gas laser. The active medium, as we already discussed, it is a mixture of carbon dioxide, nitrogen, and helium gases. The active center is carbon dioxide. We are using electrical discharge method for pumping, and electrical power supply is the pumping source. Here, the optical resonator is made up of gold-coated metallic mirror or aluminum-coated silicon mirror. The output pulse is a continuous or pulse laser. We are having both the options, either continuous or pulse laser, and the output power is about 10 kilowatt. The wavelength emitted is 9.6 micrometer and 10.6 micrometer. Both the wavelengths are emitted, and we all know that 10.6 is much more intense than the 9.6 micrometer. So before going to the carbon dioxide laser working mechanisms, we just want to deal with the carbon dioxide laser vibration modes. Since we are dealing with the carbon and oxygen molecules in carbon dioxide laser, we have to know and we have to assure what are the vibrations are taking place and how it is taking place. So we have three modes of vibration. The first one is symmetric stretching mode, the second one is asymmetric stretching mode, and third one is bending mode, or vice versa. So in the symmetric stretching mode, if you look at the figure, the carbon atom is at the center and both the oxygen atoms vibrate simultaneously along the axis of the molecule, either departing carbon or approaching the fixed carbon atoms. So this is what happening in the symmetric stretching mode. Whereas in bending mode, you know that both the oxygen and carbon atoms are vibrate perpendicular to the molecular axis of this carbon dioxide. Whereas in case of asymmetric stretching mode, both the oxygen and carbon atoms vibrate asymmetrically. That means oxygen atoms move in one direction while carbon is moving in the other direction. So the direction movement is indicated by the arrow mark in all the three cases. So these are the possible vibration modes that are available in the carbon dioxide laser. Now we are going to look over the schematic arrangement of carbon dioxide laser. So it consists of a quartz tube of 5 meter long and 2.5 centimeter diameter. This tube is filled with a gaseous mixture of carbon dioxide, nitrogen, and helium with suitable partial pressures of 0.33 to 1.2 to 7 millimeter of mercury. And this is the active medium. Both the terminals are gets connected with the DC power supply. The tube ends are coated with the NaCl booster windows. NaCl means sodium chloride booster windows. The laser light will be generated here and it will be polarized and comes as the output. So we are having provisions here to fill helium, nitrogen, and carbon dioxide laser inside the discharge tube. So this mirror is fully reflecting mirror and this is a partially reflecting mirror. Both these mirror contribute to our optical resonator. So this is the carbon dioxide laser working, and this will be the energy transition between the various vibration modes in asymmetric, bending, and symmetric mode. Here, when we switch the power supply, electrical discharge occurs in the gas. As a result, electrons collide with the nitrogen molecules and makes the nitrogen molecule to the exit state. So this is explained in this equation. Here, the electron is getting collided with the nitrogen molecule. As a result, energy is transferred from electron to the nitrogen. So nitrogen is excited. This star indicates the higher energy level, that is the nitrogen is in excited level, and electron loses its energy as a result of transferring of energy from electron to the nitrogen. Now the nitrogen molecule in excited state collide with the nearby carbon dioxide atoms and the ground state, and which excites the higher electronic vibrational and rotational level. So this can also be explained by the means of this equation. Here the energy is in the nitrogen atom, which is in the excited state, which gets interacted or collided with the nearby closest carbon dioxide atom, which is available in the ground state. So as a result of getting collided with carbon dioxide, the nitrogen atom is transferring its energy to the carbon dioxide. So as a result, your carbon dioxide is getting higher energy, whereas your nitrogen atom is losing the energy to the carbon dioxide. So if you look at the figure, we are having carbon dioxide and nitrogen. So as a result of the energy transition between the nitrogen to carbon dioxide, we are having energy transition or laser transition between the two levels, that is from asymmetric to bending mode and asymmetric to symmetric mode. As a result of transition from asymmetric to bending mode, we are getting the laser of wavelength 9.6 micrometer, whereas the transition from asymmetric to symmetric mode gave rise to the wavelength of 10.6 micrometer. So the transition between the vibrational states 001 to 100, the laser of wavelength 10.6 micrometer is emitted, whereas the transition between is 001 to 020 leads to emission of laser of wavelength 9.6 micrometer. So normally we all know that 10.6 micrometer is more intense than the 9.6 micrometer. So by means of this laser transition or energy transition between the molecules, we are getting carbon dioxide laser beam as a result of output, or this is the principle behind the working of carbon dioxide laser. Now we are going to look over the advantages, disadvantages and applications of carbon dioxide laser. So the advantages is concerned, its construction is very simple and output is either continuous or pulse. High efficiency is obtained, high output power is obtained. The output power can be increased by extending the length of the discharge tube or gas tube, whereas the disadvantage is the contamination of oxygen. We are pouring helium, nitrogen and carbon dioxide, so there may be the possibility of contamination of oxygen by carbon monoxide, which affects laser action. Also, the operating temperature plays an important role in the output power of the laser. Both the reflecting plates may be resulting in corrosion, and if it is accidentally exposed to our eyes, it causes damage to our eyes. So these are the major disadvantages of carbon dioxide laser. As far as application is concerned, we are using carbon dioxide laser for material processing such as welding, drilling, cutting and soldering. Also low atmospheric attenuation, that is 10.6 micrometer, we will be using that wavelength for open air communication, remote sensing, and also in the medical purposes we are using in the treatment of liver and lung diseases, neurosurgery and general surgery, microsurgery and bloodless operations can be done using carbon dioxide laser. So this is the major working principle, mechanism, advantages, disadvantages and applications of carbon dioxide laser. So as of carbon dioxide laser is concerned, we have to concern about the stretching, whether it is symmetric stretching, asymmetric stretching or bending stretching, and what is that, and what is the transition between these energy level which will give us to the output wavelength of 10.6 micrometer and 9.6 micrometer. So this is about the carbon dioxide laser. Now we are moving towards the output process. Okay. As far as output is concerned, there are three figures which is given. The first one deals with the continuous output, whereas this green color line is your output. If it is continuous going, so it can be called as a continuous, and a repetitive pulse output. If you see here, the output is plotted at the time, it is plotted with the output and time. Your pulse is continuously repeating, so we are calling it as a repetitive pulse output. And if it is a single pulse output, means only you will be receiving only a single pulse. So these are the major three difference between the continuous output, repetitive pulse output and single pulse output. Now we are moving to the second part of the laser, that is semiconductor laser diode. So we all know that as far as semiconductor is concerned, we will be having the PN junction. Okay. So likewise, here also we are having a specially fabricated PN junction diode, and the laser is forward biased. It means you are having positive side connected to the positive terminal of the battery and negative side is connected to the negative terminal of the battery. This condition can be called as a forward bias. So we are having the band structure here. It can be called as a conduction band. It can be called as a valence band. Normally at higher temperature, your valence band will be filled with holes because your electron from the valence band is already makes a transition to the conduction band. So as a result of these, the recombination of an electron hole will give rise to your output that can be called as emission of photon, or in other words, it can be called as a laser emission. So this is the schematic diagram of your semiconductor laser diode, whereas you are having upper electrode in the top surface and lower electron in the bottom surface, and you'll be having the p region as the top surface and n region is the bottom surface, and this can be called as a p-n junction, where both the p region and n region will meet eventually, and the charge carriers will cross each other. As a result, your laser output will be coming. Here also, as we said here, it is a forward bias because the positive region is getting connected to the P terminal, whereas your negative region, that is the bottom portion, is connected to the negative terminal. This is the metal contact, and this is the schematic diagram of semiconductor laser diode. So before moving forward, let us see the principle behind the semiconductor laser diode. It is a function junction diode, as we all know that it is a forward bias. So the electrons from N region, because electrons are the major concentration in the N region, and the holes in the P region, that is the holes in the major concentration or major charge carrier in the P region, cross the junction and recombine with each other. That is the recombination process. So as a result of the recombination, the light radiation will take place. As a result of this, we are calling it as a photon radiation or laser beam. So the photon emitted stimulates further electrons and holes to recombine. That can be in other words, we can call it as a multiplication. Okay, multiplications of photons. So this simulation makes further electrons holes recombination. As a result, your photon gets multiplied. So as a result, you will be getting stimulated emission. A strong, intense laser beam will come out as a result of this stimulation by means of a first emitted photon. So if you look at the figure, this is a junction layer or active layer. You are having P type and N type. As a result, your charge carriers will move each other. At this point, your charge carriers will meet each other. They will recombine here. As a result, your laser beam will come out of this region or the bottom region, depending upon the fabrication. So this is the energy level. As I said earlier, the conduction band is higher energy level and valence band is the lower energy level. Here you are having electrons. Here you are having holes. If it is crossing the junction, the holes and electrons will recombine. As a result, your output will come as a laser radiation. That is intense laser radiation. So this is the construction. We all know that the active medium is made up of PN junction diode. That is the single crystal of gallium arsenide. The crystal is cut into the form of plater of thickness 0.5 micrometer. The platelets, two parts having an electron conductivity N type and hole conductivity P type. The electrical voltage is applied to the crystal by means of this terminal. As a result, the optical resonator will get excited, and through with the emitter light comes out. The end face of the junction diode are well polished so that it acts as an optical resonator. So as a result of PN junction diode is getting forward biased, electrons and holes are injected into the junction region. They recombine with each other. Recombination produces radiation. This will stimulate further radiation by means of electrical voltage increasing. More and more light photons are emitted. So as a result, light production becomes stronger. That we call it as an intense laser radiations. Photons move and getting reflected between the two phases. So after gaining enough strength, laser beam of wavelength of around 8400 Armstrong is coming out. So this is the conduction band. This is the valence band. As I said earlier, free electrons are there. This is holes. When these electron is coming to the down valence band, they recombine with each other. As a result, your laser light is getting clouded. Though the energy difference between these two bands can be called as a band gap or energy gap, in which it can commonly denoted as e to the base g. So now we are going to calculate the wavelength of the laser light emitted. So we know that the relation which is given by E is equal to h nu. So h is the Planck's constant and nu is the frequency of the emitted light. So we know that nu is having the relation with the velocity of the light and wavelength of the light. So we are substituting nu is equal to c by lambda in the next step. So we are having Eg is equal to hc by lambda. So we will be cross multiplying lambda here and we will bring down the Eg here. So we can write lambda is equal to hc by Eg. So as of semiconductor laser is concerned, similar to the carbon dioxide laser, they are also having some advantages and disadvantages and applications. So the advantages are they are very small in dimension. The arrangement is simple and compact. It exhibits high efficiency. Laser output can be easily increased by controlling the junction current. Operated with lesser power than the ruby and carbon dioxide laser. It requires only very little auxiliary equipment. Continuous wave output or pulse output can be produced like carbon dioxide laser. The disadvantage is concerned, it is difficult to control the mode pattern and mode structure of the laser. So we are having some modes in designing the laser. So the mode pattern and mode structure is a major disadvantage of the semiconductor laser. And also the laser beam, though it is a laser beam, it has a large divergence like ordinary light. The threshold current density is also very large. It has poor coherence.